For 60 years, humanity has been building telescopes that could detect planets around other stars without ever actually seeing them. The techniques were indirect, watching a star wobble because a planet was pulling it, watching a star dim because a planet was passing in front of it, watching a star's light split into colors because a planet's atmosphere was absorbing specific wavelengths during a transit. These methods are extraordinarily powerful. They have produced nearly 6,000 confirmed exoplanets. They have revealed planets smaller than Earth and planets larger than Neptune. They have found worlds in the habitable zones of their stars and worlds so hot their surfaces are liquid iron. But in every single one of those nearly 6,000 discoveries, what astronomers detected was the effect of a planet on its star, not the planet itself. The planet was always inferred, never seen. And then, on June 25th, 2025, the James Webb Space Telescope captured a single orange dot in the upper right corner of an infrared image, and everything changed. That dot was a planet, not our planet, not a planet in our solar system. A world orbiting another star, 111 light years from Earth, made visible for the first time in human history by the most powerful space observatory ever built. Its name is TWA-7b. And what its discovery means for the search for life, for the future of astronomy, and for the question of whether we are alone, is a story that the scientific community is still working through a year later. The difficulty of directly imaging an exoplanet is not a matter of telescope quality. It is a matter of geometry and physics. A planet orbiting a star is, from Earth's perspective, sitting right next to something that is millions or billions of times brighter than it is. Imaging a planet next to its star is like trying to photograph a firefly perched on a lighthouse from several miles away at night, with the lighthouse blazing at full power and the firefly producing its faint glow right at the lighthouse's edge. The star's light floods the detector, drowns out the planet's signal, and leaves nothing but glare where the planet should be. Every previous direct imaging success in the history of astronomy had required planets that were extraordinarily easy targets by this standard. Gas giants 5, 10, 15 times the mass of Jupiter, young enough to still be glowing brilliantly from the heat of their formation, orbiting their stars at enormous distances where the angular separation between planets and star was large enough to separate them in the image. The lightest planet ever directly photographed before a TWA-7b weighed approximately 600 times what Earth weighs, roughly 2 Jupiter masses. TWA-7b weighs approximately 100 Earth masses, about a third of Jupiter. That gap between the previous record of 600 Earth masses and the new record of 100 Earth masses is not a small improvement. It is a factor of 6, and it means that the class of planets now accessible to direct imaging has just expanded dramatically, reaching down towards sizes and masses that are far more scientifically interesting for the questions that matter most. The star that TWA-7b orbits is itself part of what made this discovery possible. TWA-7, also known as CE Antillae, is a young red dwarf star, approximately 5 to 10 million years old, located in a loose grouping of young stars called the TW Hydrae Association, one of the closest regions of recent star formation to our solar system. Red dwarfs are small and cool by stellar standards. TWA-7 has about 55% of the Sun's mass and produces far less visible light. That comparative dimness matters enormously for direct imaging, because the contrast ratio between a star and its planet, the number that determines how hard it is to see the planet next to the star, is smaller for a dim star than for a bright one. A planet of a given temperature and size is relatively easier to detect next to a dim star than the same planet would be next to a star like our Sun. The youth of the system helps in a different way. TWA-7b formed approximately 6 million years ago, an infant by cosmic standards. At that age, a planet is still glowing from the heat with its own gravitational formation, a process called Kelvin-Helmholtz contraction, in which the planet's own weight compresses its interior and generates heat that radiates outward in the infrared. TWA-7b's surface temperature is approximately 47 degrees Celsius, warm enough to glow detectably in JWST's mid-infrared wavelengths, even at a distance of 111 light years. In another billion years, it will have cooled to temperatures that would be completely invisible to even JWST's instruments. The discovery happened now, because this is one of the narrow windows in TWA-7b's existence when it is still warm enough and close enough to detect. The instrument that made the detection possible is JWST's mid-infrared instrument, or MIRI, equipped with a 4-quadrant phase mask coronagraph. A coronagraph works by blocking the light from the central star before it reaches the detector, creating an artificial eclipse inside the telescope that suppresses the star's overwhelming glare and allows the faint light of surrounding objects, including planets, to be detected. The 4-quadrant phase mask is a specific coronagraph design that divides the focal plane into 4 quadrants, introducing phase shifts in the star's light that cause it to destructively interfere with itself. The waves of starlight cancel each other out, while allowing off-axis light from planets and disk material to pass through relatively unaffected. Even with this coronagraph in place, residual starlight leaks through and creates a speckle pattern on the detector that can mask or mimic planetary signals. The research team, led by Dr. Anne-Marie Lagrange of France's National Center for Scientific Research, applied advanced post-processing algorithms to subtract this residual starlight, stacking multiple exposures and using the rotation of the sky relative to the telescope to separate the fixed speckle pattern from any real astrophysical sources. When the subtraction was complete, a point source remained, a single faint orange dot at a position 1.5 arcseconds from the star, corresponding to a physical separation of approximately 50 astronomical units. The dot did not move with the speckle pattern. It moved with the star. It was real. The confirmation that the detected source was actually a planet rather than a background star required crossing multiple independent thresholds. The team checked proper motion, comparing the source's position against earlier very large telescope data from different epochs. A background star would have remained fixed while TWA7 moved along its trajectory through the sky. The detected source moved with the star. It was physically associated with it, not a chance alignment. The source's brightness in MIRI's mid-infrared band was then compared against atmospheric models for planets of various masses and temperatures. The luminosity was consistent with a planet of approximately 100 Earth masses at 47 degrees Celsius. The position of the source was compared against dynamical simulations of what planet is needed to produce the gap structure in TWA7's debris disk, the ring of dust and rocky material surrounding the star that had been extensively studied before this observation, when a planet of the detected mass was placed at the detected orbital distance. In the simulations, the resulting disk structure matched the observed disk geometry with remarkable accuracy. The planet was predicted by the disk before it was found in the image, and the image confirmed exactly what the disk predicted. The scientific implications of what TWA7b represents begin with what it demonstrates about the capability of direct imaging going forward. Before JWST, the floor for directly imageable planets was roughly 600 Earth masses. JWST moved that floor to 100 Earth masses. The Nature paper reporting the discovery noted that MIRI's detection limits, based on the noise floor of the actual observation, are sensitive enough to have detected planets as light as 25 to 30 Earth masses, roughly the mass of Neptune, at TWA7b's orbital distance. That is not a theoretical projection. It is a measured detection limit derived from the real noise and the real data. JWST is not just capable of finding Saturn-mass planets like TWA7b. It is potentially capable of finding Neptune-mass planets at wide orbital separations from nearby young stars. Neptune-mass worlds at the kinds of orbital distances that correspond to the outer regions of planetary systems, where the frozen, volatile, rich material of a protoplanetary disk accumulates, and where giant planet formation through disk instability is most likely, are a class of planet that has been almost completely inaccessible to any detection method. Transit spectroscopy cannot find them because they do not transit in predictable orientations. Radial velocity cannot find them because their gravitational pull on their host stars is too small to measure at large orbital separations. Direct imaging, at the sensitivity JWST has now demonstrated, can find them. And finding them answers questions about how planetary systems form at large distances from their stars that have been completely open for lack of any observational data. The connection to the search for life is less direct, but no less important. Every model of how life might arise on another world begins with the question of whether that world has the right chemistry: carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, in the right proportions and the right molecular configurations. The building blocks of that chemistry come in large part from the volatile rich material of the outer solar system, the ices and organics that accumulate far from a star where temperatures are cold enough to preserve them, and that get mixed into the inner solar system through impacts and gravitational dynamics. Understanding how volatile rich the outer regions of other planetary systems are, and whether large planets in those outer regions are delivering that material inward toward the habitable zones of their stars, is part of understanding whether the chemistry of life is common or rare across the galaxy. TWA7b sits at 50 astronomical units, well into the cold outer zone of its system, and it formed in a disk that JWST's observations confirm is still actively evolving. The planet itself is not a candidate for life, but the system it inhabits and the information its detection provides about what outer planetary systems look like and how they are structured contributes directly to the statistical framework that will eventually tell astronomers How many inner solar systems have the volatile delivery history that made Earth's chemistry possible? Dr. Lagrange, in the ESA press release accompanying the discovery, said that TWA7b is the first exoplanet light enough to be directly photographed, and that this result marks a new chapter in the direct imaging of exoplanets. Co-investigator Aaron Carter of the University of California, Santa Cruz added that we have only just begun, and that there are many more images of exoplanets to come that will shape understanding of their physics, chemistry, and formation. The extremely large telescope, the 39-meter ground-based observatory under construction in Chile, expected to see first light in 2028, will extend the direct imaging capability to even smaller and cooler planets around nearby stars, eventually reaching the mass range of super-Earths around the nearest stellar systems. And the Nancy Grace Roman Space Telescope, launching in September 2026, will conduct a coronagraphic technology demonstration that paves the way for the mission after it, the habitable worlds. Observatory, the next flagship space telescope, whose primary science goal is the direct imaging and spectroscopic characterization of potentially habitable Earth-like planets around Sun-like stars. The orange dot that JWST captured on June 25, 2025, is the first pixel of what will eventually become a catalog of directly imaged worlds, a library of planets seen as they are, not as the shadows they cast across their stars. The most fundamental shift in how humanity looks at other worlds did not arrive as a dramatic announcement or a crisis or a moment of shock. It arrived as a single faint dot in the corner of an infrared image, and in that dot, everything changed. The Princeton University laboratory of Marissa Weichman, funded by the National Science Foundation, is building a specialized spectrometer designed to measure the light absorption of fullerene molecules and other carbon cage structures in the laboratory, specifically to provide reference spectra for JWST and future infrared observatories. That work sounds esoteric. Its purpose is direct. Every time JWST points at a distant planetary system and measures the spectrum of light from a planet or a protoplanetary disk, it is looking for specific molecular fingerprints that identify what the material is made of: water, carbon dioxide, methane, ammonia, and potentially, in the future, oxygen in combination with methane, the biosignature pair that in equilibrium requires a biological source, because no known abiotic chemistry maintains that combination against the chemical reactions that would otherwise destroy it. Getting the reference spectra right, knowing exactly what each molecule's fingerprint looks like at the temperatures and pressures relevant to planetary atmospheres, is the work that makes the difference between detecting a biosignature and misidentifying noise as one. JWST's detection of TWA7b proved that direct imaging can find planets at the mass range where those signatures become meaningful. The question of what is in their atmospheres is the next chapter, and it begins with the single orange dot that appeared in an infrared image on June 25th, 2025, and changed what it means to look at another world.